Have you ever wondered why it takes so long to understand definite integrals in your math class? Well, instead of spending a whole semester, you're only going to need a few minutes for this video, so ninja kick that like button and let's get started. Huh! We've got the integral here of x plus 1 over x plus 2 dx, and one thing I want you to recognize is that this is a definite integral because you have what's called the limits of integration. Pi is your upper limit here, and 0 is your lower limit. And so when you solve this, I like to take the normal approach and solve this as if it wasn't a definite integral first, and then plug in the stuff at the end. Now, for this particular integral, x plus 1 over x plus 2, I have another video where I actually show a really cool shortcut. I'm going to do the same thing in this video. I like to rewrite x plus 1 in the numerator as x plus 2 minus 1, because then you'll notice that when you break up this fraction into two parts, you've got this x plus 2 over x plus 2, which will simplify to 1. And then for the second side, you've got 1 over x plus 2, which will just be dx over x plus 2. And what's cool now is for the right-hand integral, you can then use a very simple U-substitution. Now, my approach here is I'll drop the limits of integration and focus on solving this integral first, because I don't want to be plugging in u and x when solving the definite integral at the very end. So the integral of dx over x plus 2 can be rewritten as the integral of du over u, because we use the U-substitution. And you remember that the integral of this is simply the natural log of the absolute value of u. So to make sure we don't have any hiccups at the end, let's go ahead and put everything back in terms of x. Remember, u is the same as x plus 2, so we'll go ahead and plug that back in. Now remember, we just solved the right-hand integral. We never solved the integral from 0 to pi of 1 dx here. I rewrote it because we don't want to forget that that's part of our solution. And when you solve that left-hand side, you're going to get x, right? Because integrating 1 dx is simply x. Now you're going to be evaluating this x from 0 to pi along with the right-hand side, which we've already solved. It's going to be evaluated from 0 to pi as well. And this is where the fundamental theorem of calculus comes in. Remember, when you integrate something, you're getting some parent function. And when you have these limits of integration from pi to 0, it's the same as f of pi minus f of 0. Where f is this final parent function that we found using integration. And what this means then is you're going to take this upper limit pi, you're going to plug it in everywhere you see x, taking that result and subtracting it from doing the same thing, but now plugging in 0 everywhere you see x. I like to make sure I'm using these brackets here in parentheses properly, because you want to make sure that you don't accidentally add where you end up subtracting and vice versa. So I put brackets around the whole first part, and wherever I see x, I plug in pi. That'll give me pi on the left-hand side when you evaluate x from 0 to pi, minus the natural log of pi plus 2, because for x, I plugged in pi there as well. I put brackets around the whole thing and subtract it from another term that has brackets around it, where everywhere you see an x this time, you plug in a 0. So we're going to go ahead and simplify this. This will give you pi minus the natural log of pi plus 2 plus the natural log of 2. Two things to note here. The absolute values drop because it doesn't make sense to leave an absolute value of positive numbers here, right? Secondly, this is why the brackets were important. Notice how on the right-hand side, you have a minus minus that becomes a plus. Had we not used brackets properly, we would have had minus natural log of 2 and we'd be wrong. And so when you want to simplify this further, I personally like to rewrite it as in parentheses natural log of 2 minus natural log of pi plus 2. Because by putting the positive natural log term first, I can use a property for the natural log of a minus b, because that's the same as the natural log of a over b.